So in the previous video, we got to see how batteries can maintain steady state electron flow through a circuit. And here I would like to take a look at what happens if our electrons flowing through the circuit encounter some sort of element that provides resistance to that flow. Generically, we call such devices resistors and say they exhibit the property of resistance, which we are going to look to characterize. Now, this resistance to flow can take many forms. In practical electronic devices, it's often achieved by replacing the wire with a material that has lower mobility of electrons, like for instance graphite or something like that in the case of many commercial resistors. But it can even just literally be a constriction. So for instance, in this photo of a light bulb here, you can see where the big arrow is pointing. There is a very, very thin tungsten wire that is connecting the two much larger metal posts. So it turns out that charge can flow rather freely through the posts without any significant hindrance, but it's very challenging for it to go through that filament. And in fact, the electrons will collide with the partially shielded nuclei in the filament, impart a lot of kinetic energy, and which in turn heats up the filament, and then it emits that energy via radiation, and that's how an old style incandescent light bulb worked. So what we see here is just me modeling that constriction. So over here, I'm looking at a wire, and over here, the other wire. And then in between, I have a filament. So I've already drawn in that I want my conventional current flow to go from left to right, but in all of our materials, any material that you're going to choose for a wire or a filament, the mobile charge carriers are going to be electrons. So which way are the electrons going to be flowing in this circuit? Yeah, to the left. So we'll have our conventional current flowing to the right, which means that our electron current is flowing to the left. All right. So I already mentioned, and we will look into this in more detail in a future video, that in a typical wire, our electrons are not moving very fast at all. So they're drifting very slowly. We will label this VD for the drift velocity. And it'll be quite slow in this region here. Now, as it's drifting along, very occasionally it is going to collide with an atom and basically come to almost a stop. So we do need some sort of a force to keep it moving. What's going to be providing that? Pause and get back with me. Yeah, it's going to be from the fringe field of the battery that this must be hooked up to. So going all through here, there must be, I'm just going to draw like a single line to represent it here, a fairly weak electric field going everywhere through this when I first turn on the switch before the light bulb starts glowing. All right. So now imagine that you are an electron right here after I just threw the switch. So there is a very weak rightward pointing electric field. Which way are you going to move? Pause and get back with me. Yeah, you're going to be moving to the left. So what happens here when this electron lands here? Believe it or not, it's just plain stuck. It can't go anywhere. And so when you first energize the circuit, you wind up all the electrons that are immediately next to the constriction wind up forming a sheet of charge all along the edge there. By the same token here, the mobile electrons get pulled off here and leave behind a residual positive surface charge along the part of the wire that's not hooked up to our filament. All right. So then any future electrons that come in, what's going to happen is they're going to see this wall of negative charge here, and they're going to get kind of repelled down and into the constriction. And then likewise out here, as they exit, they're going to be attracted away from the constriction, and so they will end up doing some sort of trajectory like that. Okay. But what this means, though, is that we've built up a very big electric field here across the filament, right? Got a lot of positive charge on the one side, a lot of negative charge on the other side. So we actually have a very strong electric field in the vicinity of the filament. And this is a good thing, because thinking back to fluids, if fluid flows through a constriction, does it speed up or slow down? Pause and get back with me. Yeah, it would have to speed up, because incompressibility of a fluid required that the same volume of fluid go through in the same amount of time. Here, we're not so worried about volume of electrons, but number of electrons. I mean, however, once we've built these surface charges here, then from forever after, however many electrons go flowing into here have to come out of here, which means every second that same number have to be passing through here. So because this is a lot tighter constriction and we're trying to shove an awful lot of them through, they have to be moving faster through here. So our drift velocity is much greater. So our electrons actually carry a lot more kinetic energy going through the filament. And so that's why when they collide with the partially shielded nuclei in the filament, the collisions are more violent and it heats up the filament a lot more than it heats up the wire. The wire does get heated up a little bit. This is why electrical codes have minimum wire gauge requirements depending on how much current is flowing through them, in order to keep the number of collisions with partially shielded nuclei every second to a manageable number so that the wire doesn't overheat and melt. With the filament, in an old style incandescent light bulb, you're going to have to choose materials that are more tolerant of it. That's why tungsten is a popular choice. But the idea is that, yeah, you make it very hot and then radiate off that energy into light. Now, why is it so hard to find an incandescent light bulb for ordinary use anymore? Well, it turns out that it wasn't that practically speaking, it was a waste. 85% of the energy radiated as light was radiated in the infrared, where it wouldn't let us see anything. And only 15% was being radiated into the visible. So once affordable compact fluorescent bulbs and then later LED bulbs became available, it became mandated that we only have incandescent bulbs for certain specialty uses in order to reduce the actually fairly substantial load on the electrical grid that comes from our needs for lighting. If we put it all into the visible, we can use literally about a sixth of what we would with the old style incandescent bulbs. So that's why we don't use them anymore. So all that to say, though, I want you to think. So we've got the electric field inside the wire is much stronger than outside. So this does mean, like I've alluded here, if I draw a free body diagram, here I will have a very significant electric force And our collisions with the molecules, I'm just calling a kinetic friction for lack of because I don't want to call it phonon exchange, which is what it is. Not photon, phonon, but we can just call it friction for our purposes. Whereas here, the electric field is quite weak, so the electric force was quite weak, but again, it was all it needed to offset the relatively small amount of friction, if you will, because since you weren't moving as fast, the collisions were less violent. Okay. So, in fact, in practical devices, most of the time we get away with saying that that in steady state, the electric field of the wire we acknowledge is not zero, but compared to the resistive devices, it's pretty darn close. So what this will mean is that for practical purposes, you can go with modeling all of the voltage drops as being across the resistive devices. So across here, we have an electric potential difference because we have an electric field strength. We will call that delta V across our resistor. So in order to, our figure of merit for describing the resistance of the device is that would be more resistive if you have to make this electric field, and hence the voltage required bigger in order to drive a given current through. So we define the resistance to be the ratio of the voltage applied across the resistor to the current that potential difference drove through the resistor. So once again here, the units, since we have a combination, it's a volt per amp. This gets called an ohm. It's named after Georg Simon Ohm, and that actually is his name, OHM, just 3 letters. However, the annoying thing is the symbol for the unit is the uppercase Greek letter omega. And this is done for the practical reason that an uppercase O can look a lot like a 0, which would be very confusing. So basically, when you draw an uppercase Greek omega, you're just drawing yourself a horseshoe, but you make sure to point it so that the good luck is raining out. Okay. So for typical devices, just to get an idea of a range, a wire might have about 1/10 of an ohm of resistance. And when you start pulling resistors out of a box, they'll start in the single digits of ohms, and they'll work their way up to around about 100 mega ohms. Is usually about the biggest I've ever seen anyway for a typical device. I'm sure somebody somewhere has done something more pathological. Now, if we go ahead and plot the voltage required to drive a current as a function of the current that we are attempting to drive. I know we should probably draw this the other way, but I'm trying to keep the idea of what the slope might mean. It turns out not to be a straight line. The typical shape for a lot of devices, although some devices are just plain weird, but the typical shape for a lot of devices is a cubic kind of shape. And what's going on here is that if we have a low current, when an electron hits a partially shielded atom, it's just basically, it won't move around very much. It'll wiggle just a little bit. But when we have a high current, because we're imparting so much to the So we're imparting so much energy in our collisions to the partially shielded nuclei. What will happen is that the partially shielded nuclei will pick up a greater thermal energy. And so what happens is they vibrate more violently in place. This is sort of like, you know, watching a guard in basketball. When you see them kind of wiggling back and forth, they're trying to effectively make themselves bigger to make it harder for, say, the forward to power on by and go in for the layup. It's the same sort of idea here. Once these partial shielded nuclei have taken a fairly good beating from all of these energetic electrons, they'll be wiggling around more violently, which paradoxically increases the probability of future collisions, just like that basketball guard. I'm trying to draw the foul. So as we jack up the current, it turns out that the voltage required to be applied across the resistor goes up disproportionately with the current. However, and like I say, generally tends to follow a cubic sort of shape. However, within any cubic, there's a region near the origin where this looks linear enough. So we'll say this is nearly linear. And if we pinky swear to just operate our device in this range, this gets called the ohmic region of a device. And for an ohmic device, we can then model the resistance as being a constant. So in general, it's not. As I go up, once I get outside the ohmic region, the resistance here in the ohmic region is the slope of the line here. But then as I go up here, it's just the slope of whatever chord I strike from the origin to that point. So that slope gets ever greater and greater. So Ohm's model, and I prefer to call it Ohm's model rather than Ohm's law because I'm about to go onto a bit of a rant for that. Ohm's model says that if the device is ohmic, So it says that if the device, and that's a big if, is ohmic, then we can say that the current that goes through is directly proportional to the voltage applied across the resistance, and inversely proportional to the resistance itself. Because physicists like to write equations as effect equals cause, here the current being driven is the effect, and the cause is the applied voltage and the resistance of the device. This is the physically strict way to write it, but often you'll see us get away with writing it like this. And this is because you can remember it with the mnemonic twinkle, twinkle, little star, delta V equals I times R. So if the device is ohmic, we can go ahead and say that the resistance is a constant, and we can treat it that way. So then, for instance, we can just look at something like, say, let's say that I hook up a 100-volt battery. Across a resistor. A squiggly line thing here means a resistor. Don't draw loopies. Loopies are actually a different device. So if you're drawing resistors, draw them with squiggles. Do not draw them like this. That is actually a different thing that we will encounter later. So let's say that we have a 10 ohm resistance here. How much current is going to be going through the device? Let's say this is positive, this is negative. So then the conventional current will flow that way, from positive to negative. outside the battery, and then inside the battery it will flow from the negative terminal to the positive, because remember, it's a complete loop. So we can remember twinkle twinkle little star, delta V equals I times R. Here we want the current, so I will equal delta V over R. So it'll be 100 volts over 10 ohms is 10 amps, which is a decent chunk of current, but totally reasonable. I mean, a typical household breaker in the United States is set to trip at 15 amps, so that's not an unreasonable amount of current to be drawing. Alrighty, we will continue these thoughts into the next video series, so have a good one.